probably the happiest days of my life are days when I have a book and I don't know of any errors in the book yet. And it's especially important to me today because this book is about my life's work. I mean, if somebody would ask me what I thought I maybe do best and have spent most time on, I would say it's something that I've always liked to call the analysis of algorithms. And this book takes about 3 dozen papers that I wrote about the subject over the last 40 years, and then I got a chance to go over them all again and fix them, and also make it so that take out embarrassing things like when I use a sexist pronoun or something like that. And so with all the formulas, I could type in the left-hand side and the right-hand side to a computer, and now we can evaluate it and check that the formula's right, and I could fix the ones that were wrong, and also at the end of most of the papers, I added something to bring them up to date, or supplementary material that I thought would be interesting. And anyway, I'm happy about this, and I hope some of you like it too. It's got a beautiful cover, and of course you can't tell a book by its cover, but I do want to show you the back cover. Can you zoom in on that, Lance? I just want to see how good the zoom is here. Because I've dedicated this book to Professor De Bruijn, N.G. De Bruijn, or Dick De Bruijn, those of you who know him, in the Netherlands, because he has been my guru, the person who, ever since I got my PhD, I considered him my postgraduate doctoral advisor. Every time I had a problem that I got stuck on, I would write to him, and he would send me back a letter, would help me get unstuck. And that's been going on for almost 40 years now. So I dedicated this book to him, and what I want to talk to you about today is one of the things that he has spent most of his life on, asymptotic methods. First, I'll show you the table of contents. The first paper is the paper that I gave at the International Congress of Computer Science in 1971. That was one of these 1-hour addresses where you sort of get a chance to talk about your life's work, and that's where I sort of thrust this topic on the world. And my wife, on the occasion of that conference in Ljubljana, it's now called Slovenia country, she made this nice title for my slides, and I've always liked it, so I've had this up in my office at Stanford all these years. And I even now on the web you can download the PostScript file that will give you that. And she also made another slide for me that tells why I like analysis of algorithms, and a few others that she made for me that I've lost. But these are anyway. I thought I'd show you those today. I probably should have put them in this book. Maybe next printing will do that. First error. Okay. The second chapter goes the other way and says how dangerous computer science theory can be, while the first one says how wonderful it can be, and so on. It covered lots of different topics, and some of them are highly technical, others are more formal, are less formal, and a lot of them are about average case studies of how well computer methods work on average. Others are about the worst case and the complexity theory of all methods to solve a problem. How good could they possibly be? At the end of these papers are mostly about complexity, and something of interest to those of you studying computer science now might be chapters 28 and 29, which was when the subject, what we call now NP problems, NP hard problems, and so on, when that terminology was invented. And it includes comments of many people at the time when we were trying to come to the grips of what should we call this topic that looks like it's going to be pretty rich. And anyway, that's the general outline of the book, and I want to talk today mostly about supplementary material that I did for Chapter 21. It's a paper I wrote in the 70s with Arnold Schoenhager, who's now at the University of Bonn, and it was one of the, and we solved a problem about a what we call it the equivalence algorithm. Nowadays it's more often known as the union find problem. The question of if you're given pairs of elements that are supposed to be equivalent to each other, can you tell whether or not two others are equivalent by a chain of the elementary equivalences that you've been given? It's also the same as saying are two things in the same component of a graph, if you know if you're given the edges of the graph. So and we showed that if you take a very simple algorithm for the problem, and if your data comes in at random, the average running time is going to be at worst proportional to the number of points that you're considering the equivalence of. But we didn't know that the constant of proportionality. Now, is Steve Simon here? He said he was going to come. Maybe maybe the traffic is bad. He's a professor at Hayward. But after we wrote our paper, let me see, Chapter 21 I want to get to. Okay, so after we wrote our paper, really nice extension of our results was done by Steve Simon and Bela Bulabas at Cambridge University, and they published their paper in the Siam Journal of Computing 1993, where they identified. Arnold and I had proved that that this is linear time on the average, but they found what the constant was. So they nailed the constant as being this. C is the sum of these terms, and I'll talk about these terms more in a minute. So that was a great result, but it also put me into a little bit of a dilemma for the consistency of my book, because every time I refer to a fundamental constant in my books, I've always tried to evaluate that constant to 40 decimals. So, for example, if you look at the Art of Computer Programming and you look at the in the back of the book tables of fundamental constants, here you have square root of 2 to 40 decimal. Square root of 3, e, pi, Euler's constant, log of pi, things like that. I give it to 40 decimals. I didn't have room for 50. This is a 9-point type to be room, but on a regular page you didn't have room for more. So anyway, this was about, and I calculated a lot of these in the 60s. But ever since that day, whenever I had a new constant, it wouldn't feel right to have it at 10 places or something if it was a fundamental constant. In fact, this turned out to be scientifically important to have constants to many places, at least 3 times in my life. One time, for example, I was working on the problem of factorization. It's one of these other chapters in the book here, and I was trying to calculate the average size of the largest prime factor of a random number. If you take a number, about a 100-digit number, and then you want to say about how many digits are there going to be in its largest prime factor, and you can find the average length of it, and it'll be about 62 digits. And let's see, I have an example. Where is that analysis of a simple factorization? Oh, that's the previous chapter. So that's So for example, if you look at the numbers, where are we here? Yeah. So if you look at the, for example, 100 largest 10-digit numbers, these would, and you can say how many no, this is number of prime factors. I wanted to say how large are their prime factors. Anyway, it turned out that this constant 0.62 was the average number, but I also in the course of this work calculated another constant that I needed as I was doing a numerical integral associated with it, And I looked, and we had computed this constant by some long, very hairy numerical integration involving additive formula, and we got, it came out to 1.78107 something or other. And 2 weeks later, I happened to be in the library looking up in a completely different problem, and I was looking at a paper by Rosser and Schoenfeld that was about prime number, and they had a constant in there that had a feeling of deja vu. 1.78107. Have I seen that somewhere before? So I went to my office. I wrote down the constant. I came back to my office and I looked, and sure enough, that was the constant that we had calculated by this long numerical process. But the thing was that Rosser and Schoenfeld didn't call it. They called it e to the gamma. So I said, oh my goodness. Could it be e to the? I better check it, because they only gave the constant to 5 or 6 decimals, and so I remember my excitement. I ran to a telephone, so that in those days you had to go through a modem in order to connect to MIT in order to compute on the Maxima program at MIT, and so I could log in over there, and the phone wasn't working, and so finally I got connected to MIT, and I said, okay, now I'm going to calculate e to the gamma. So I turned to the tables of numerical quantities in my book, so I could look up gamma, and I could type in the value of gamma, and I found out, oh, there's e to the gamma too. And it agreed to 15 decimals with our result, and then it disagreed in the 16th decimal. And so I said, now wait a minute. Would God create a universe in which there could be 2 constants that arise naturally and would agree to 15 decimals, or would God be able to create such a universe? So we checked our program, and we just couldn't find any error in it whatsoever. But finally, we realized that we had used a numerical method that depended on continuity of the 5th derivative, and this function had only 4 derivatives, and it was discontinued. So this was the first time that I learned that doing high precision calculations can help you. First of all, it helped me discover a whole connection, because once I knew it was e to the gamma, that meant a whole new kind of mathematics must be connected with this problem, and then I started seeing other things pouring on it again. The other thing is this constant 0.62. It turned out we had that was difficult to evaluate, and we had one of our grad students, Bill Mitchell, who was a student here in the 60s, and he evaluated it to 40 decimals for me so that I could put it in my book, and it turned out that we found out later that in the journal Math of Computation, in the following year, some number theorists evaluated another constant, also to 30-some decimals, in connection with in connection with this prime factorization problem. As far as I knew, the constant that I asked Mitchell to do was for the size of the largest cycle in a random permutation. And so if you have permutation of 100 elements, and it's a random permutation, what's the longest cycle? And it turned out to be about 62 long. And so in the same journal, 1 year apart, the same constant had been evaluated, but they didn't know it. In fact, it had gone through a whole different chain of editors. And it wasn't until I wrote my paper on factorization 10 years later that we looked back and found out that these were the same constant. And so there's another case then where knowing a constant of high precision first gives you a conjecture, and then later on we can see the mathematics comes on. Now the third story, I'll tell you quickly, arose with the calculation of greatest common divisors, and Richard Brent had worked out a theory for what we call the binary algorithm for greatest common divisor. And in the previous edition of my book, I had quoted his 12-digit value of the fundamental constant that arises in that analysis, and it was here 0.70597. And I wrote to Richard and said, look, I've got this is the only constant I don't know to 40 decimals. Can you possibly calculate it further? Because he's got all these supercomputers in Australia where he could work. And there was another constant too here, 0.39. So we have these constants now. So while but I didn't get any answer from him. So I said, well, okay, I better try doing it myself. And so I looked at his paper, and he had given two methods to evaluate this constant in his paper. One method, well, there were two completely different methods, and they both gave the same answer to 12 digits. So he was pretty confident of the thing. So I started to use one of his methods, which was based on power series, and I evaluated lots of constants, and I worked for a couple of weeks and got lots of digits, and I got this answer. And here again we were disagreeing, but this time in about the 14th decimal place. And from his results and mine, we were only up to 30 digits at the time, but here we thought there must be a bug in we started the people at Wolfram Research in Illinois were going to help us check to make sure that we were going to check every step of the way to find out what kind of a discrepancy could happen. And finally, it turned out that we both noticed on the same day independently a mathematical error that Richard had made in the 70s in his paper. And he had neglected a tiny little term that affects only the 14th. It has no effect until you get to the 14th decimal. So his mathematical formula for one of the two cases gave, in fact, a different result than the formula in the other one. It's very similar to the story of when Hardy and Ramanujan were studying the prime number theorem. Ramanujan had a formula that he thought was correct, and there was some little wobbles, some little wave effects that have a very small thing, which finally Hardy and Ramanujan did when noticed when they published their rigorous proof. So finally, Richard, with massive computation, was able to calculate these constants to 40 decimals, and I was getting another digit every 2 days from him in email, and then Brigitte Vallée in Caen in France was working on a really wonderful theory of this problem, and she has the best results by far in it now. And she has this conjecture that the two constants that I showed you actually are related. One over the other is twice log of 2 over pi squared. And that is still a conjecture, but we know that it holds to more than 40 decimals now. Okay. So that's why I'm kind of interested in having numbers to many places. But so here I had this constant now, and I thought, okay, I better evaluate it. But I looked can we zoom up on this close as you can, Lance? So it's pretty hairy formula. I have to sum this from 1 to infinity. And it's 1 over m minus this hairy summation, which involves factorials in two ways and huge numbers that are sort of supposed to cancel out, and that should cancel with the 1 over m. And it turned out that t sub m is of order 1 over m to the 3/2 power. So we're summing some. So I can certainly evaluate this for small m. M up to 1,000 or something like that, and exactly. It's not no big sweat now on a computer to work with rational numbers, and I could add up t sub m up to a ways. But if I have t sub m is proportional to m to the minus 3/2, that means that the sum, a remainder after n terms, is going to go like 1 over square root of n. So even after I've done 1,000,000 terms, I've only got 3 digits of accuracy. Now, in their paper, Bolobash and Simon gave a value for this constant to 6 decimals. And I say, well, wait a minute. How were we able to figure that? You must have known. You must have used some other tricks that weren't in your paper. So I called up Steve. Steve, are you here yet? Yeah. Oh, okay. Hi. So you can check me out. You can verify this. We'll stand up anyway. We'll get you on camera here. So the TV man didn't get you, but that's, well, you can pose later. Anyway, so what I remember you telling me on the phone was that you had worked on for a couple of years with computers at 3 different universities to get this value, and you talked to a lot of numerical analysis analysts, and they said, well, we have certain acceleration methods, but it wasn't. But it was kind of a real adventure to get 6 decimals. Is that a fair summary of?
I talked to one numerical analyst at Cambridge, and he tried some acceleration methods which did not work. It did not converge.
Okay. So one numerical analyst at Cambridge had given advice. Yeah. So, but I didn't have too much confidence in that I would ever be able to get it to 40 decimals. But it was a fun challenge, and in fact that's part of the thrill of the chase was sort of there. I wanted to say, could there, I was supposed to know something about this kind of formula, so was it possible that I could get somewhere with it? But also I didn't really believe that your 6 digits were correct. I thought probably maybe 5. But I was going to at least I wanted to at least verify that it was correct before I put it in the book. So I started looking at the problem, and today I want to show in the rest of the time some of what went on. I can't give you all the, if you're really interested in details, it's actually 10-page addendum to chapter 21 in the book. But I want to summarize the highlights, the general principle. I'm going to talk about 7 general principles that help in asymptotic problems that I found useful in this particular case. So now first I've got to simplify this formula a little bit. If you look at the very end here, it has this factor 1 over 1 plus delta km. Now delta just means that if k is equal to m, this factor is 1/2. Otherwise, the factor is 1. It's a complication and it messes up the formula. So I'm just going to forget that. I'm going to leave off the last term. We can always. It's only one term. I can add it back in later. So I'm going to only sum from k1 to m minus 1, and then I get rid of that factor. But we still got some factorials in there. But anyway, I can work on this sum. Because the m, it's a sum on k that has k to the k minus 1 over k factorial, k plus m minus 2 factorial divided by k plus m to the k plus m minus 1. I'm showing you from a piece of paper now. I guess I could really use the real book to do this, but it's the same, of course, in the book, because the paper was my proof for the book. All right, now, so principle number 1 that we're going to use on this problem is good old Euler's summation formula. It's a simple idea for how to convert a sum to an integral. Then the integral gives the first approximation, and then you also know the error between the integral and the sum. And you can carry that usually a lot further and get better and better corrections to evaluate the sum. So and this is described, of course, in lots of books, including my own. And one of the most famous results of that is Stirling's approximation for factorials, which is obtained by Euler's summation formula. So people learn in high school that n factorial is asymptotic to n to the n over e to the n times square root of 2 pi n, and then there's other corrections if you want to go into further details. So after you've got this first part of Stirling's approximation, then you've got other terms that go on, 1 over 12n, 1 over 288n squared, minus 139, so on, and the coefficients that I'm going to call it sigma sub j. Sigma 0, sigma 1, sigma 2, the constants in this approximation. I use sigma because, it's sort of S for Stirling. But they come from a formal power series that if you take the exponential of something involving Bernoulli numbers, you get this, and then you get the series of which defines all the constant sigma. And it has a nice property that that also 1 over n factorial will be e to the n over n to the n square root of 2 pi n. And then the rest of it goes 1 minus 1 over 12n plus 1,288 n squared plus all the odd-numbered coefficients change sign, but the same sigmas occur in the asymptotics of 1 over n factorial as in the asymptotics of n factorial. And the reason is that obvious from this power series because it has only odd powers of z in it, and so if we take the reciprocal, everything just changes from z to minus z. Now, I should mention that this series, I have dot 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 in here, but it's asymptotic. It's not really equals. It's asymptotic because it doesn't converge for any value of n. These sigmas eventually start oscillating and growing so that the series diverges. If I take n equals 1,000,000, these terms will get smaller and smaller and smaller for a while, and then they come to a point where of diminishing returns where they start diverging and going all over the place. So it doesn't. So it gives you a good clue about the size of 1 over n factorial, but it doesn't give you any infinite number of decimal places. It only gives you a certain number based on how big n is. But that's asymptotic. Now, step 1 was to use Stirling's approximation. So then I could take my sum Sm that I had, and I could rewrite it instead of having a k plus m minus 2 factorial. It was simpler to say k plus m factorial, and then divide by k plus m and k plus m minus 1, and so I get by simple transformations, I get it into the form of a sum of other sums involving a constants tau sub j, which are the sum of the first j sigmas. Now, in order to get this second formula, I used another principle. So first I used auto summation formula in order to get to get Stirling's approximation, say, and then the second principle here was what I like to call thinking big, which means if you're looking at if you're trying to figure out how this sum behaves when m is a big number, you try to imagine that m is really huge. You don't think of m as being 100, but you think of m as being 100 to the 100th, or something, Google. And then you would say, well, but k, maybe k isn't so big, so k plus m, k plus some huge number. It's better to factor out that as a square root of m. So I take a square root of m out of this, and I make this 1 plus k over m in the square root. And similarly with the denominator, and I get some formula of this form, and the larger, so by thinking big, it suggests the transformations that I made to put it into this form. And so instead of evaluating the sum Sm, which I needed for my original problem, I've got it reduced now to a sum of other problems which involve 1/2 minus j. Which I'll call beta. So I have to evaluate a bunch of other sums for various values of beta. Beta equals 1/2, 3/2, 5/2, 7/2, and so on. Yeah, let's see, because j starts at 1. So mathematics tries to take one problem that you can't solve and replace it by another one that you might be able to solve, or a bunch of other problems that you might be able to solve. And here I've replaced it by an infinite sequence of problems of this form, which are looking simpler than the one I had, because there's no factorials left in here. It's just powers and stuff. Now, but now what next? Well, the next thing is to apply. I have to look at De Bruyn's book on asymptotics because I was stumped. I had no idea what to do. And so De Bruyn has a chapter on what do you do if you have a sum that you want to get the asymptotic value of. And he says, well, there are four cases. There's case A, case B, and case C, which are pretty easy. And then there's case D, where those don't apply. And this turned out to be in case D. But he had a good idea in case D. He didn't give it a particular name. It was his case D, but I think we could call it break off an approximation, or break off, well, whatever, break off an approximation. So in other words, you have something that you don't know what to do with, but you subtracted an approximation. And then you try to deal with the degree of approximation. This is a little bit related to a method that Laplace invented, which we call trading tails, but it isn't the same method. So what we're going to do here is actually we're going to take our unknown sum Sm of beta, which I'm just going to call S, Sm. Well, let me give it a sketch of it. Sm of beta is a sum from 1 to m minus 1 of something that involves beta. There's a minus beta in here. And now, but I don't know how to deal with that one. I can call that S. But I can try adding this. I can try instead to go for the sum all the way to infinity, which we could call S plus S prime. Add the other terms, because maybe they aren't going to make a heck of a lot of difference. If I kept K going further and further, but maybe they will. But now I have an approximation to S. The individual terms of S here, it was K to the K minus 1, e to the minus K over K factorial. I did have a factorial left in there. Now, I know 1 over K factorial is approximately something, K factorial is like K to the K. So this looks like K to the minus 3/2 power divided by square root of 2 pi times the sum of these sigma. This is Stirling's approximation again. So if I subtract off Stirling's approximation up to a certain degree L here, then I've got I've got something that's maybe easier to deal with. So I'll call that A that I'm subtracting off, and so I have A. So I have Pm of beta, which is going to be the sum from 1 to infinity of these terms minus the approximation. So P is going to equal S plus S prime, the whole thing, minus A prime, which is the approximation up to m minus 1, and the approximation for m up to infinity. And then I have to correct that. To get down to S again, I also have to add in Qm of beta, which is which I call A plus A prime. This is the sum. This is the approximation that we had. So my Qm is this approximation based on Stirling's formula, but it's something that I can probably sum up to infinity. And then I had to also, though, put another Rm, which is A prime, which is the approximation, for the large terms. And I can add that all together, and what do I get? So I take this, so I take this plus this minus this, and I'm left with S plus S prime minus A prime. And now I just have to show that this is very small. So if I've got a good approximation, if my approximation is good, which in fact it is, because if we turn the page, we'll see that that the approximation I've made here of K to the K minus 1 e to the minus K over K factorial minus the Stirling's approximation to it is good to K to the minus L minus 5/2, where L is the number of terms that I took in Stirling's approximation. And so that's on order k to a minus big power, and if I sum that all the way from m to infinity, that's the error is only m to the minus l minus 3 halves. So this is going to be 0.3. I break off an approximation, and I've replaced my original problem of SM by 3 problems, P, Q, and R. And P plus Q minus R is not equal to S, but it's equal to S plus something very small. Good enough that it goes to 0 to a high power of m. So that was part 3 in this game of trying to analyze this constant. Well, now P, Q, and R are left, and R was the one I knew I could handle. And R works again with Euler's summation formula. Euler's summation formula works best when you have when you're trying to do a sum something like this. I have a sum from m to infinity of a function of k over m. So the index of summation, so k over m sort of goes from 1 to infinity. And in this case, f of x was a particular function that I could, that's not too bad. X to the minus 5 halves. This is an example of different values of beta give you different powers in here. So Euler's summation formula says, well, you want to figure out how a sum is looking like asymptotically. What you do is you replace it by the integral, and you have other terms. And Euler's summation formula actually gives you an expression of f in terms of the derivatives of f, then with powers of m in the denominator. Except that when n is 0 in this formula, it's not the derivative of f, it's the integral of f, because that would be f to the minus first derivative, which is the integral. But basically, it gives an asymptotic series. So I take more and more terms, and I get better and better error of approximation of big O of m to the minus L, where L is as big as I want to choose. So that was going back to principle 1 again, and it enables us to check off R as a solved problem. Now I have to do Q is another problem, and for here we use a technique called Mellin transform, which is invented by Hjalmar Mellin. I think he was Finnish mathematician in the 19th century, and I never heard about this transform when I was getting into math education. I guess it was just one of these things that my teachers never got to, but it wasn't used. Now we see it as wonderful. But I first heard about it from De Bruijn when I sent him a problem. I was trying to analyze a sorting method called radix exchange sorting in the 60s, and I had gotten some empirical results so I had a good conjecture as to what the answer was going to be, but I had no idea how to prove it. And he said, well, why don't you try this? And it turned out that what he was telling me was basically a Mellin transform, a subject that he doesn't discuss in his book on asymptotics. But when I found other ways to use this method over the next few years, and then other people realized, oh yeah, this is Mellin transform that you can find in integral table books, and now it's been developed into a really powerful method, especially by Philippe Flageolet and his colleagues at INRIA in France. But when I first knew about it from De Bruijn, I put it into volume 3 in the early 70s. We call it the gamma function method because it was the way that got this gamma function into our formulas. I can give you a quick summary of what it is, but I want now to evaluate the sum of f of k over m as we had before, but not from m to infinity, like I did with Euler's summation formula, but from 1 to infinity. And I want to get a good expression for the sum in this range. And the idea is that you use Mellin transform f star of s, which is defined to be the integral of f of x times x to the s minus 1. S is a parameter, so we start with a function of x, and we get its transform, which is a function of s. It's something like a Laplace transform. And so in this case, you evaluate it, and it turns out to be a beta function. It turns out to be gamma of this time, quotient of some gamma functions here, provided that s is a complex number whose real part lies between 5/2 and 4. This is all not too hard to check. And then you use analytic continuation on this complex function to say, well, this would also be true then, not only for the things where we verified it, but also by analytic continuation, it's true for all complex values of s. Now, complex analysis was something that I'm really glad that I had in my junior year in college. I think it's absolutely the most important mathematics I ever learned, and I insisted that my daughter take a course in complex analysis, even though she wasn't doing any science at Brown University, because because complex analysis is so important. So anyway, this is just another example of how 19th century mathematics has unreasonably effective to 20th and 21st century problems. So anyway, now I wanted to evaluate this function, 1 over x to the 5/2, 1 over x, 1 plus x to 3/2. I wanted to get a good asymptotic expansion of this thing from 1 to infinity. And what you do is then you can get the inverse Mellin transform. And if you know f star of s, you can get f of x back from it. And the formula is you integrate 1 over 2 pi I times the integral over some straight line c minus I infinity to c plus I infinity, and you integrate f star of s times x to the minus s ds. And so plugging in x equal k over m and then summing gives you a formula for this sum in terms of an integral, because I could carry out the sum inside the integral sign, and I got a zeta function in here. The sum of 1 over k to the s power is by definition Riemann zeta function. So here I've got a formula that I used to think was amazing that it would arise at all. I mean, I have gamma function 3 times and zeta function once. But now I see it so often, I think, well, yeah, this is just another case where we got gamma functions and zeta functions occurring. These to me in my education were something that only number theorists cared about, and I was here. I'm using it in a problem on union find algorithm, for goodness sake. So if C is any real number between 5/2 and 4, this derivation was valid, and I can get an asymptotic series by moving the C to the left, but taking the poles of the integrand into account, and so that gives an asymptotic series, which turns out to be it involves the zeta function at negative values. So zeta of 5/2, zeta of 3/2, zeta of 1/2, where this is the extension of this complex valued function, usually defined only for values that are real part is positive, but it's also well known what their values are negative. So this is the answer then. Turns out to the Q problem. The Mellin transform gave the answer for the Q problem. I had only P to go. So what would your question?
Yep. And then an equal sign. What happened?
Because
Well, the right-hand side is equal to the thing above it. Yeah, that's right.
Yeah, okay. But yeah, I am not claiming that equal to that. Thank you, Percy. You saved me $2.56. Yeah. But I don't know how many days will go by before I find the first mistake in this book. But yeah, this is yeah. I'm not sure if this converges the zeta function of minus 5 halves. I can't remember this. This complicated transformation. I don't know how fast it grows. It might or might not be. It probably doesn't converge. But I'm not claiming that it does. But it looks like I am. So maybe I should put I should put that in there. But it is equal, which is a sort of a stronger statement, even though the series might not be correct. So that's a good point.
The point is,
What?
typography makes it look like the sum up in the upper left is equal to that.
Well, if I had a less than sign, you wouldn't say that. Okay. Well, we'll have to hash that out later. Now, so anyway, that solves the Q problem, and now the P was the one that was really, So now I was really hooked on this. I mean, I had R and Q figured out, and I still hadn't got the answer to my constant. And of course, I have nothing if I can't if it reduces it to a problem that I can't solve. But here. We come to our fifth principle for asymptotics, and that is luck. Sometimes you have to be lucky. Now, this is as I said, but if you're working on a problem that has a reasonable mathematical structure, it isn't inconceivable that it will relate to some other problem that's been studied before. And as we saw, the gamma function and the zeta function, which came up in completely different contexts, now turn out to be just what I needed for part of this problem. Well, one of so there's something called the unreasonable effectiveness of 19th century mathematics, that almost all of the problems that arise that have some cleanliness to them, if we can solve them at all, the mathematics was already worked out for us more than 100 years ago. But with one exception, there's one function that was almost not studied at all during the 19th century, but turned out to be very important in computer science, and now we're learning more and more about it all the time. And this is the tree function, which I've already talked about a couple other lectures in this series, and it's equal to the sum of k to the k minus 1 over k factorial times z to the k. And it satisfies it z, t of z is equal to z times e to the t of z. And then you can iterate this and go on and up and get an exponential of an exponential and things like this. Now this function was studied a little bit by Eisenstein in 1850, but very limited extent. So this is the one function of all the ones that I've come to know and love that more of a 20th century thing than a 19th century thing. And but I've been running into it over and over again when I'm I first ran into it. The very first algorithm I tried to analyze satisfactorily was hashing, and I ran into things like this. So I keep coming into it all the time. It's the generating function for rooted labeled trees, because there's k to the k minus 1 labeled trees with k points. Now that's why I call it the tree function. So here this function p that I'm worried about is this k to the k e to the minus k part is just t of 1 over e. And then the other part I can sum. First I'm summing all the way up to infinity. Actually, I'm going to have to cut it back to m. But the other part is just a sum of reciprocal powers of k to the j, so that involves a zeta function. Now, but the value of t of 1 over e is easy to figure out because of this functional relation that t satisfies. So t of 1 over e is 1. And this is, in fact, the radius of convergence of this series. When z is 1 over e, t equals 1, and if z gets bigger than 1 over e, this series diverges. Now, one of the first things I had to do was evaluate this sum, and it turned out to be 1 minus something in zeta functions that we could just compute. But I also have to consider not k to the k minus 1 here, but k to the k plus n minus 1, where the thing gets a lot, gets more complicated. So, for example, when n is 3, I have to take this sum, k to the k plus 2 e to the minus k over k factorial. Now that's approximately, well, let's see, k factorial is like k to the k, and the square root of k in there. So this is approximately k to the 3/2 power. So I have to subtract off 3 terms of Stirling's approximation in order to get this down to something that'll converge. And then I take off, then the next, from j equals 3 up to L, I continue on, but I have to take out the first 3 terms here in order to get something that will converge. And so now I have to figure out what's the value of this constant. If I can work out the value of this constant, then I'm done. Now I use the standard summation method to get the value of this constant. I say, well, this is the limit as epsilon goes to 0 of e to the minus epsilon times the whole thing. I multiply the whole thing by e to the minus epsilon, and I let epsilon go to 0 in order to get the limit. Because if I put an e to the minus epsilon in here, I can relate this to the tree function. And in fact, I use Mellin transform again to get this part of it. In other words, I'd like to figure out what is a sum like this, e to the minus epsilon k divided by, or times k 3/2, sum that over k. What does that look like as a function of epsilon? And use Mellin transform argument, and it gives you the answer. We're running short of time, so but you can always look it up. But now I get to something that's quite important, I think. The operator that's usually in tech it's called var theta, which is so you take the derivative and you multiply by z. You don't only differentiate, but then you multiply by the variable again. And what this does is, in a power series, it multiplies the coefficient by the power. So if you have z to the n, you differentiate and you get n times z to the n minus 1. But you multiply by z again and you get z n times z to the n. So theta is this nice thing that if I take theta cubed of a function, I've multiplied its coefficients by the coefficient of z to the n by n cubed, which is what I had in here. So now this theta operation is actually it's so nice we could have been taught it in high school instead of derivatives. I mean, like theta applied to fg is equal to f theta g plus g theta f. Theta applied to f to the x is equal to x times theta of f times f to the x minus 1. It's the same kind of rules for the chain rule doesn't work quite, but the most beautiful thing about theta is the analog of Taylor series, and this is a formula that I wish I had been taught early in life, because I use it now a lot. So that is that f of s times e to the t is equal to the sum of t to the n over n factorial theta n of f of s. And let's now if instead of theta here I had the derivative, this would say for example, f of s plus t f prime of s plus t squared over 2 f double prime of s, and second derivative, third derivative, this would be Taylor series. But instead of using differentiation, use this theta instead, and then you get the expansion of not f of s plus t, but f of s times e to the t, which is f of s times 1 plus t squared over 2, and so on. And this formula is so neat for working around saddle points and things like this. So anyway, this is a formula that I want to in fact, then there's also, if you know, there's a formula with remainder that's shown here in the book. That if you only look at the first few terms, then you get an explicit formula for what the remainder is, and so you know the quality of approximation that you get. And so what it turns out is then the following. I studied the tree function, which I had been doing it by luck in other problems, and I'm interested in knowing what does t look like, not at 1 over e, but near 1 over e. So that's the value of t of e to the -1 minus epsilon, where epsilon is some positive number. Instead of writing a positive number in here, it turns out the formulas turn out to be a little simpler if we replace epsilon by w squared. In fact, w squared over 2, where w is some real number, because then this is guaranteed to be positive. So now I say, well, this is going to be a little less than 1, so let me make this substitution. T of e to the minus w squared over 2 minus 1 is 1 minus v. Then we can expand by using the fact that t of z is z times e to the t of z, and we can determine that we get this formula, w squared over 2 is equal to v squared over 2 plus v cubed over 3, v fourth over 4. That's why I chose the things like it did. So I can now take the square root of this equation and solve for v in terms of w, and we get this sequence of constants. It's easy to do now just with one command on a computer. Say revert this series, and we get the various coefficients here. And now I set w equal to square root of 2 epsilon, and I find out the behavior of t to the e to the epsilon minus 1. And also, I can also figure the similar thing when this theta operation has been applied to it. So I can see exactly how this tree function is behaving in the neighborhood of 1 over e by this means. And this all turned out to be. It took me 2 or 3 days, but it was exciting times because I was getting these interesting numbers coming in here, and in fact, there's a beautiful result that it was amazing after because a deja vu happened all over again in this study, and that is as I'm looking at this expansion of tree function of e to the minus t minus 1, and I try to solve my problem of what are the p. It turns out that I'm getting a certain constant c sub n, which is right here in this tree function, and the numbers c sub n are shown at the bottom here. Now these are numbers that I had seen before many times in other problems. In fact, it was in Ramanujan's first technical publication. He solved a problem about half of the exponential series, and it involved these constants. And so there has to be a reason for why this is true, and that's what this part of my book is devoted to explaining. And in fact, Cecil Rousseau found a very interesting connection related to this when he's studying random mappings. So it turns out then that the coefficient of t to the k over 2 in this thing, when k is odd, is in fact also the sigmas that we were starting out from Stirling's approximation. So this formula coming from and I never knew this before, but coming from the tree function, and you look at the expansion of this reverse series here, and you look at the odd numbered places in there and multiply by the right factorial, and you get Stirling's approximation, the constants of Stirling's approximation. Wow. In fact, that's the kind of thing that keeps me going. Even though I said I retired and I'm not going to do mathematics anymore, I'm just going to write up other people's stuff. When you start seeing patterns like that, you just have to look at it a little closer. So I was doing this as a tribute to De Bruyne's to De Bruyne. It's not to his memory. He's very healthy, and when the books arrived last week, he got the first copy of the book, of course. We shipped it off to him. So now the point is then that in this expansion here, you see this 139 that occurs in the numerator there. That's a strange prime number. Well, that was also when I first gave the table of the sigmas for Stirling's approximation. There's that 139, and that was a dead giveaway that something was connected. And if you see the number 139, think again. That was principle number 5. Having some luck and combining with the other thing, then principle number 6 was use computer algebra. The main problem with doing asymptotics in the old days was that you would make mistakes, and it would get, in order to get more than 2 places of accuracy in asymptotic calculation, you had to fill many pages of paper, and chances that you'd gotten it all correct were getting smaller and smaller all the way through, and it was boring, not that much fun. The fun part is seeing these numbers and getting them to work out. So here we got computer algebra in there, and so I now get to get the answer. I had that S is equal to P plus Q minus R, and I have to add this up for all the different values of beta, a big matrix of things, massive cancellation occurring here and there, and then I have to sum the S's because those are the T's, and we had to sum the T's in order to get the constant. But putting it all together, I got the value of the S as an asymptotic series here, and you'll notice that I did have an equal sign here, Joe. But I put ... So maybe that's my cop-out. I should do in the other place here. Because, in fact, I know this series does not converge. A lot of these, like Stirling's thing, doesn't converge. But it's very good, depending on how big M is. And that's the S. And then the T, similarly, I get formula for T sub m. So I said T sub m was approximately of order m to the minus 3/2 power. And I have to now, so I've got this asymptotic formula for T, and I want to get the exact value of the sum of the T's. Well, there's an old trick that you use for that, which is to just take the exact value up to m equals 100, and then use the asymptotic value after m equals 100 or something. Or so here I don't know if I used 100. Actually, I used several different values of m. That's a good way to find out if you've made a terrible error. If you get 2 different answers based on the threshold between the exact and asymptotic. But ta-da! Finally, you get the value to 40 decimals, and Steve's result was absolutely correct to 6 decimal places. But I was glad that I could bring this up to the same standard as all the other constants in the book. So I said there would be 7 principles of asymptotic analysis. Well, maybe I could stretch this a little bit, but let's just say that the last one is rest and enjoy after your work, because now you can tell other people about this constant. It goes on the web, and that's another good reason to know things to large precision, because now you can use it to find any paper, mathematical paper. You can compute the reference to it. But if it's about a sequence, you can go for the online encyclopedia of sequences, and if it's a real number, you want to say, has any paper been written about this number? Well, you just type in the number, and it says, oh yeah, because we can use these numbers to index the literature. And then but then a little bit of rest, and you're ready for another problem. Okay. So that's my story about this, the joy of asymptotics. I'm glad to answer any questions you might have. No question. Well, you have to read the book if you do have a question. Yeah.
Book available?
Is the book available? What's the story on that, Lowry?
Yes. Outside.
Outside, there's a table that Yes, in fact, sure, I got a pen here. I'll sign it for you and date it, and it'll, you can auction it off at eBay. Yeah. Susan.
I would like to insist on the fact that what you said about looking up on the web, it's not just a joke. That is, you can't right now. You can't look up a formula on the web because there's all different kinds of ways of typesetting it and everything.
Yeah.
You can look up 139 or...
You can look up numbers, but formulas that appear in many different guises.
Yeah, that's right.
In fact, I remember one time when I was talking to Maurice Niva, and I decided that he was that reminded me of French Impressionist paintings, because he said, Don, did you ever see this formula? And he wrote it down, and there were typographic errors in both the left-hand side and the right-hand side of the formula, the way he wrote it down. But I had seen the formula before, and a lot of times, in fact, you don't even, your formula might be sort of vague, you're not quite there, but information retrieval, people can do it, but there's no canonical form. Well, the hypergeometric series we have canonical form for, and this book, or what's his name? The guy from Lockheed. His tables of series. Eldon Hansen has a fairly good canonical form where you can look up a formula, and so if you look up Eldon Hansen's tables, I have a copy. I use it rather a lot, you have a formula you want to check out for a series to see if it's. He'll get you to the literature on that, and he tells you how to find it in his table of contents. Still, it's limited to the kind of things that you can canonicalize like that. Yeah.
How hard is it to say what the problem, where this started? I mean, there was some. You said it was a union.
Oh, union find algorithm. So this is the algorithm where you're given. It's like the connectivity problem in graphs, and the constant is how much work do you do in order to find connect up the entire graph, and essentially it's this: whenever you get a new edge in the graph, you add up the size of the edge between components that aren't connected. You add in the size of the smallest of the two components. So if you're connecting one point to a large component, you just get one. If you're connecting two components of size 10, it's 10. If you're connecting a 10 with a 20, it's 10. And it's the sum of those which is going to be then proportional to C times the total number of vertices in the graph. So most of the time you're adding, you're picking out a fairly short component to the total. And the reason that we're interested in the smaller number is that in our data structure that as we're merging these components together, we say, well, whichever one is smaller, we have to do an update on all of our entries in the smaller one to say that they now belong to the big one. So that was the simple algorithm that we analyzed, and that's what this constant. That's what this constant 2.08477 is all about. Okay, well, you have just enough time to rush out and buy the first copies of this book.